Welcome to the network layer. Finally, we've reached the network layer, the core layer of the internet, the layer that really keeps the internet together. So what is the idea? Well, now why not connecting all those local area networks, metropolitan wide area networks, and this actually creates the internet? Brilliant idea. Well, there's a problem. So as we've learned, those local area networks, metropolitan, etc., we use different technologies. Yes, we've seen we have Ethernet, but we have our OTNs, we have still some legacy networks, we have different data rates, etc., frame formats, sometimes also different link layer addresses, media. We could do some of the jobs here also on layer 2. But the question is, how can we really transfer data across many different networks, wide area, local area, from one host end to end to another host? And one first solution is we need an address, a uniform address. So we have to know how do we address a system, and we need a packet format. So how should packets look like? And we should abstract all these lower layers, so the link layer and below. So we don't care about the technology. So our packets, now we really call them packets, not frames anymore, but packets, they have a certain address. And this address really defines the destination of the packet across all the technologies. So we have a common end-to-end packet format, and we are independent. Okay, great. So one address for worldwide reachability, one packet format. There's another problem. Problem 2, how do we find a host across this now really big network? So it's not a local area network anymore. We cannot broadcast, for example, and then to find someone, so spanning tree and whatever. So how to do this? So how do we implement now the communication between A and B? So now we have the job to deliver a packet that originates from one computer across switches and routers across this network, many other networks, to some other computer B, whatever. Or maybe to several computers, or maybe etc., etc. So broadcasting, as I said, that's not scalable. Absolutely not. We have millions of hosts. So maybe setting up a state in all those switches here, so to set up a certain path, or we do something like the spanning tree protocol, absolutely not scalable. And this is not efficient to have a worldwide spanning tree. So this is why we have a closer look into routing and forwarding. So routing, that's basically how do we find the next hop information? It's quite important. How do we update this for each destination? So for each destination worldwide, we have to find the so-called next hop information. So we have to know where to forward in the next step incoming packets. And we'll see that there's a big difference between routing, so setting up a certain table with different paths, as we will see, and the actual process of forwarding, how we move incoming packets really fast within some nanoseconds from an input interface to the appropriate output interface or interfaces in case of what we see multicast. Okay, so let's start with this big chapter. So first of all, what are the fundamental goals of the network layer before we then have a closer look into addressing, IP, the protocol design, how we assign addresses, map them, error control management, a bit about network address translation, routing, and multicasting. So the fundamental goals. Well, obviously, the network layer, here our layer 3, here has to deliver packets end-to-end, so end-to-end connectivity across different other networks. Yes, we know applications want to communicate, but we know we always go through all the layers down to the physical layer and up again. As you will see, we have routers in between, and the routers, they go up to the network layer, and they may process packets here. So for now, we have a closer look into this layer 3, and there we define certain network identifiers, we define the packet format, and we define how we perform routing and forwarding. Before we have a closer look into what we do in the internet, first of all, there are different philosophies how you can do that. The two basic ways are connectionless, that's the first one, and the second one is connection-oriented. So what is the idea here? Connectionless end-to-end communication. Well, we talk about packets, and the packets can have variable length. And each of the packet has at least a destination address. Yeah, it might be a good idea also to have a source, but think of a postcard. A postcard, you have to have at least the destination, a stamp on it, and then you can write whatever you like. So if there's a source address on it or not, that's not important for the postal service, but here typically in our packets we have a source and a destination address. Furthermore, we don't need any reservations. That's quite important. So if you want to send your postcard, you just drop it in the box and that's it. And then the service somehow handles the postcard and delivers. So you can send something spontaneously, no reservations. Okay, that sounds nice. There's also another way. And the second way is called connection-oriented end-to-end communication. There we have three phases. First, you establish a connection. That's the first step you have to do. Connection establishment. So for example, you dial a phone number. So that's the first thing you do if you want to call someone. You dial a phone number on your mobile phone. Then you can talk, you can transmit data, information exchange, and then you hang up the phone. That's the third phase. So we have three phases: connection establishment, data transmission, connection termination. So you cannot spontaneously transmit data, but you always first have to set up a connection. Okay, so there are pros and cons for this. So for the connectionless, as you can imagine, it's very easy to implement. Remember, you drop your postcard, write the destination address, valid stamp, and that's it. Very easy. The problem here is you can reorder the postcards, your packets. So, okay, you may have differences in transmission delay. Maybe someone drops a postcard. It's not reliable. Plus, we may have varying paths for packets, so it depends on certain load characteristics. So that's a certain challenge. We see how we can handle this. But big advantage, easy to implement. So for connection-oriented communication, well, we have to do this reservation, but then we do not change any sequence. There's no out of order the delivery, so we know actually where the traffic flows, but it's more complex to implement. So what happens if a connection breaks, then everything breaks, etc. So connection-oriented is a bit more complex, and we will see layer 3, the internet, does connectionless. So IP is connectionless. But we'll also see that layer 4 offers with TCP connection-oriented communication, like telephone network with connection setup phase and teeing down the connection, etc. So indeed, you can implement a connection-oriented service on top of a connection-less service. Okay, but for now, we mainly focus on connection-less communication because that's the way the internet does it on layer 3, and here we are on the network layer, the layer 3. What else do we have to think of? Well, we have many so-called intermediate nodes. So you have your end system, the hosts, connecting to this cloudy thing, networks and many networks. And inside we have many of these, what we later will see, call them routers. Routers connecting everything. So routers are at the core of the internet. You also have a router at home. Your DSL modem typically has a router integrated. So What do we need? So intermediate nodes, they, well, have at least to have some state. They have to know something about the network, as we'll see. They do not know the whole network, but we'll see the intermediate nodes at least know some paths. They have to limit broadcasts. Maybe also they have to guarantee certain quality, as we'll see. So maybe you have more important packets and less important packets. Okay, so they need some knowledge at least inside the network. But we want to limit it. Why? Memory is limited. So you cannot store arbitrary amount of state. So you cannot learn what is the topology of the internet, or where are all the destinations, where are all the hosts, where are all the subnets, etc. So we have to aggregate, we have to compress states. We'll see how this is done with the help of a nice addressing scheme. Then also throughput is limited. So we cannot allow arbitrary amount of control traffic, for example, to exchange state so that all those routers talk to each other all the time to exchange certain state about the network. We will see there are certain routing protocols and algorithms that have to exchange some state, but there's a limit on it. So we need some approaches that do not talk too much. And also computing capacity is limited. So a router is a high performance device. So operating at terabits per second, yes, but still computing capacity is limited. So plus the forwarding across a router should be in the range of nanoseconds. So the simpler, the better. And we will see how the new protocols really reflect this. So the routers have to do less. That's the idea. To have a higher capacity in packets per second they can process. So for routers, it's not that important to see how many bits per second they can transfer. It's more important to see how many packets per second they can process. Okay, so we'll see during this chapter where this is needed, where we have to be really fast and where we can be a bit more relaxed. So let's start looking into the details. First of all, we need addresses. We'll see how the classical IP version 4 works, and then we'll also have a look into IP version 6. Those are the two versions of IP running in the internet. Okay, addresses. That's important. Addresses, we need them. We have to identify end systems. So this is the unique address you have in the worldwide internet. Okay, so a host also may have several addresses. Then we needed to select the right interface. What is important about addresses? So we could think of many addresses. For example, don't we have MAC addresses? Don't the computers already have their unique address? We have these nice 48-bit MAC addresses. Oh, that's a good idea. Why not using them? We will see that those addresses need to be in a structure where they allow certain compact representation. Also some kind of how can we compress when we store addresses in routers, how can we compress this somehow? Furthermore, those addresses should be independent from the hardware, from the link layer. Because maybe we have a single address on layer 3, but maybe different addresses on the layer 2, where maybe you have a wireless layer and Ethernet layer 2, etc., etc. So furthermore, the addresses should support the finding of a path, and we will see how we do this in a decentralized manner. There is no central instance, no central super duper cluster compute center that actually calculates, computes the paths for all the packets. This has been done decentralized, and they have to be unique. And typical examples on layer 3 are the IP version 4 addresses, well known to many of you, around since many years, almost 40 years, and the bit newer IP version 6 addresses around since the mid-90s, and there are also some other addresses. So layer 3 addresses, we'll have a closer look into this. So what is important and why can't we simply use MAC addresses? Oh, if you compare, whoa, MAC addresses, they're even longer than the IPv4 addresses. Extremely important, aggregation. Addresses have to allow aggregation in the network. Why? We have intermediate nodes, many of them here, this and this cloud, here in between, many of these routers, etc., and here, so many intermediate nodes. So now we assume we have 3 computers on the left side with the addresses AB, AA, AC. You see immediately what do they have in common? The A as the first letter. And we have 3 computers on the right hand side with BA, BB, and BC. Now, why does this help? Well, because in this case we know, oh, all the computers on the right, they have B something, B star. On the left we have A something. That means in the middle we will have a simplified table that only says, okay, all the A, whatever follows to the left, and all the B, whatever follows to the right. Without this, aggregation would have to store, oh, there's an AA, and there's an AB, and there's an AC going to the left, and there's an BA, a BB, and a BC going to the right. So that's more. So you see 3 entries compared to a single entry. 3 entries compared to a single entry. And this could be even more. You can compare this a bit with the phone numbers. You all know that you have a country code, for example, 49 for Germany. Then you know all the phone calls starting with the 49, they go to Germany. Then Germany should handle this. Then you have a, for example, mobile operator code. And then you know, okay, this number then goes, for example, to T-Mobile, and then they have to handle this. And then you have the number of the subscriber. So you have hierarchical addresses. And that's the trick behind this ability to aggregate the addresses. So we can do aggregation based on geographical aggregation, like the phone numbers. That was the basic idea. Phone numbers, like, well, this is the country, geographical area, and you have a quite strict assignment policy. Okay, that's what you need for Germany. 49 plus 1 is the US, and so on, and so on. So that's quite strict, geographical, so countries. Well, we can also think of hierarchies based on organizations, sub-organizations, etc. That's a bit more flexible when you think, okay, maybe you have a company that works all over the globe and some other companies operating in different countries, then maybe you aggregate addresses by the organization, so that one organization starts with A and then something, and the other starts with B and then something. So yes, this is a bit more flexible. So it depends on, for example, the company who runs the network, the subnetwork, as we'll see. Then all the addresses start with the same bit, the same numbers. Bit more flexible, but maybe also less compressed compared to this strict country and then city and then subscriber. Or in the case of mobile phones, you have the country and then the mobile phone operator and then the subscriber. Okay, so aggregation, very important. So hierarchical addressing, that's the important thing. And we will see that when an organization asks for addresses, you will get a range of continuous addresses with a certain prefix. So that's the starting part. Then in our example, it was this A and then whatever may follow, or the B and then whatever follows. So you have a certain prefix. That's the term, prefix. And that's the idea that you then can say, for example, there's an international organization that distributes the first letter in this case. And then maybe if you have a star given to a national organization, then this national organization can say, okay, I can then give away the AA, whatever then follows, and the AB and whatever follows, and the AC and whatever follows. So we can have more hierarchies. And from this AC, then for maybe a university gets this and then can say, okay, the ACA then goes to math, and the ACB goes to chemistry, and then within chemistry and within math they can do something with their computers, with their addressing. This is what we will see for IP version 4 and IP version 6. So you can recursively delegate authority over parts of the address space. That's the idea. And then sooner or later you have to assign the address to an interface. And what you do inside the network, and that's how you benefit from this aggregation, you try to match what we call the longest common prefix when you try to find a path to the network. How does this work? So you're inside the network, you're acting as a router, and if you want to know where should your packet go, we will learn during this chapter that we have to find the longest common prefix, and we then pick the output interface that shares the most digits with the destination. How does it work? So, okay, on the left hand side, we ask for, okay, this address A, B, C, D, etc. And this is the host. We will see that inside the networks, these larger systems, for example, so-called autonomous systems, we'll learn more about this, they announce the address ranges where they know the destinations. So the upper cloud may tell, I know exactly where AB star goes. And the low one says, yeah, I know where all the A stars go. And what you do now, after these announcements, if you have to send a packet, and inside the packet it says it goes to ABCD, you check, the router will then check, okay, in which direction did I receive the longest prefix? And that's the upper one. Why? Because there I received the AB and then star. We will see how this works, and that's one of the key ideas, that we have addresses that allow for aggregation, and if we want to establish a path, we follow the path based on these announcements, and we always pick the longest common prefix that matches. And that determines the best path. That's the idea. We'll see how this works. We'll then also see where we do this during the routing process, how we fill routing tables, and how we create forwarding tables based on this. So, but here we're still at this very general introduction where I say, okay, hierarchical addressing, that's important. And these are all reasons why we cannot use MAC addresses. MAC addresses are flat. So they're assigned based on the manufacturer of the interface. So you cannot assign them based on some geographical ideas or organizational ideas, etc. What else is at least a challenge? Well, addresses, security. What happens about address spoofing? So if someone claims to own a certain address, we'll see this works on many different ways. So this works inside a local area network. We see how this someone can do this, but also on a global interdomain level. So someone can simply claim, I know the perfect short path to a certain destination, and then all the packets will go this perfect short path. The problem is that due to scalability reasons, we do not have a global secured database. It's a fully distributed system. There is no single database telling us this is the state of the internet and this is where all the packets go. That's impossible. And we'll also learn it depends on your vantage point how the internet looks like. So it depends on where you are, in which network you are, which paths the routers will show you to a certain destination. What else is important? Efficiency. We'll see that, okay, we want to aggregate. Okay, but this requires address planning. So a good aggregation would be, oh, I have a large address block. So I want to keep this and then I can do whatever I want internally. The problem is this wastes a lot of addresses, and we'll come back to this when we see, okay, no more IP version 4 addresses. So you have to give back addresses if you don't need them, but that's sometimes a problem then with the aggregation. And we also see that we have to do this all in kind of an automated fashion. So no one wants to do this manually. So all the address assignment, picking the right address, etc. So we will look at some of the solutions later in the chapter. That's just the intro. So some very general questions. So, I mean, we had these MAC addresses, and hey, MAC addresses, perfect. We have 48-bit. 48 bits, well, that's, 2 to the power of 48. Many addresses, great. But why can't we build the internet then based on these addresses? And this also, well, it's quite close to the next one. So what are the basic requirements for the layer 3 addresses? And that's exactly something layer 2 does not fulfill. We also saw the advantages and disadvantages of connectionless and connection-oriented. So remember what are the advantages, pros, cons, and find examples for both. So there are good examples for both, and there are good reasons for picking one or the other. The internet, layer 3, is always connectionless.